Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullah. Peace and blessings upon you all. Dear students, today we're gonna start our new chapter, that is a deadlock. Okay, so we're gonna see inside out the deadlock. We first see what deadlock is, how is it, how deadlock occurs, and then we try to see what are the prevention mechanism and deadlock avoidance, detections and preventions and all those things. Okay. So firstly, we should understand what deadlock is all about. Say for example, I give an example. For example, you want to write. So if you want to write, what you need a copy. Say this is a copy, and you need a pen. Okay. Now you have two people who are coming together, and they both want to write. Now what happened is A has occupied the copy, and simultaneously B comes in, but he occupies the pen. Now A is occupying the copy and it's asking for the pen, while B has occupied the pen and is asking for the copy. Okay, so now A is saying that, okay, I hold the copy and I want a pen. I'm not gonna leave the copy at all, but it waits for B to leave the pen so that it will have copy and pen and start writing. And B thinks that, okay, I got a pen and I need a copy which is being occupied by someone else. B waits for someone to leave the copy so that it can start writing. Okay, so in this situation, A is waiting for the pen, B is waiting for the copy, and A is not leaving the copy, B is not leaving the pen, so they are in a state of deadlock. Okay. Okay, now for example, if there were two, for example, pens. Okay, in this scenario, A can get the pen from this side. Okay, and after that it will finish writing because it gets now the pen and as well as the copy. Now it can finish and leave the copy, and B can run later on. Now this is not a deadlock situation. So in a deadlock situation, uh, we should be holding something and waiting for something, and that too in a circular fashion. Okay, say for example, another example I will give you, there are some trains. Okay, say one train goes on this side, so this is a train for example, and another train goes on this side. Okay, so it goes on this side. For example, another train is in front of it. This train want to go on this side, but this train is in front of it going this way. This is going on this way, and there's another train on this side. Okay, it want to go on this side, but this train is in front of it and it want to go this side, and another train is going this side and it want to go this side, right? And it can go this side, but this train is front of it. So what will happen? This is a situation of deadlock. This train can go only when this train can go, but this train can go when this train can go, but this train can go only when this train can go and leave the space. Okay, so they are in a perfect state of deadlock. What is happening here is one train is occupying this track and asking for the another track, okay, which is being occupied by the other train, and that train is occupied this track and asking for this track, and this train occupies this track and asking for this track, and this train occupying this track and asking for this track, and this is in a circular fashion. So when we have this situation, we are in a state of deadlock, because I can't leave this but I want this. This guy says I can't leave this but I want this. When this train gets this track, then and only then can leave this track. Okay, but the problem is nobody is gonna leave its own state, so that means it will not actually leave the track for the other train, so they will stay it for the ever. Only solution is that this some of the trains need to backtrack. Okay, or you got to kill that train. Okay, maybe I got a Spider-Man and I ask Spider-Man to grab this train and throw it away, maybe, and then we can have a free space. Okay, so this is a situation deadlock where uh, we are having some processes occupying some resource and asking for another resource. But to be a deadlock, okay, we need to have some conditions. Now these are the four important conditions to be there, so that there will be a deadlock. Now all of these conditions should be true. Okay, so all of these four must happen simultaneously for a deadlock to occur. The first one is mutual exclusion. That means one or more than one resources must be held by a process in a non-shareable exclusive mode. That's what we are saying here, is that if we want to have this track, the two trains cannot simultaneously walk on this track. Okay, for example, if we say another example, if we have a book, okay, and there are two boys who want to read, they can simultaneously read from the book or from the board. So this, there is no mutual exclusion. Okay, or for example, I say there is a washroom. Now a boy goes to the washroom. Now two boys cannot go simultaneously to the washroom. The first one has to go to the washroom, then only then the next one can go to the washroom. So that means this need to be have a mutual exclusion. Okay, so you are holding this washroom. Okay, this is what we say, that you are having one resource must be held by a process in a non-shareable manner. This is what is done by this train. This train has held the track, and now that track cannot be simultaneously occupied by this train. So that is what we need to have a mutual exclusion on that. Now hold and wait should also be there. That means you are holding this track and asking for this track. This guy is holding this track and is asking for the track occupied by this train. So hold and wait should be there, right? So all of these conditions need to be there. Then there should be no preemption. No preemption means you cannot leave this track. If for example this track can be, for example, we have a disappear button on a train, this you right click and disappear, this is gone. That means you can this train can go on. That means uh, you can preempt it. But say for example here you are in a washroom, if you can preempt it, leave it for a while and give it to this guy, then we can say okay, this is preemptible. But the washroom is non-preemptible because the resources are of two types, either preemptible, non-preemptible. Okay, for example, there is a printer, like an example of washroom, I will say printer. Now process 1, say for example process 1 comes in, this is process 0 and this is process 1. Both of them want to print. Okay, say this wanna print a leave, some document, okay, and this wanna write some other document. Now if I am writing something here, is the document of P0, okay, now I can't preempt it, because if I preempt it, now we will have a piece of page where one word is from the P0 and another word is from the P1, or one line is from the P0 and another line is from the P1. That means this whole document is of no use. So that's what we say, that this printer is non-preemptible. So if you are holding such a resource which is non-preemptible, because if you are holding a resource which is preemptible, then you can leave it, then there's no problem. If you are holding the if this train is holding the track and it can leave it, then there is no problem, there is no deadlock, because it can leave it so that others can use it. But if the situation is you cannot leave it, say for there is no reverse button, reverse gear in this train, for example, so you can't leave it, you have to go forward only. So in that scenario, it is a deadlock. Okay, so this is the third condition. All the three should be, if one of them is not there, it is not a deadlock. And that too, the last one is the circular wait. Like we say here, A is waiting for the train B, B is waiting for the train C, C is waiting for the train D, and D is back waiting for the train A. So circular wait. there should be a circular wait. So all the four conditions should be true so that deadlock will be there. There's one more thing called as a starvation. So we should not confuse starvation with the deadlock. Okay. In starvation, for example, this is CPU, and there are processes coming on. There is priority. So P0 is coming. So it is of low priority. Say P1 comes with high priority. So P0 is put in a sleep queue, and P1 is given the CPU. Now we think after P1 finishes, we give P0, but in the meantime, P1 finishes, P2 comes in, which is again a high priority to the P0, and so on. And then P3 comes in, P4 comes in, and the process start coming in. They're all in high priority than P0. That means P0 is starving. But there may be a chance, maybe not right now, maybe after a long time, but P0 will finally come and get the CPU. So P0 is starved, not deadlock, because in deadlock you got no chance of coming out of the deadlock. So when you're in a deadlock, that means you have got no chance coming out of it. Okay. So for a deadlock to occur, all the four conditions should be there: mutual exclusion, hold and wait, no preemption, circular wait. If one of them is not there, it is not a deadlock. There's one more thing called live lock, which we saw in our algorithmic solutions also. In deadlock as well as live lock, the process is doing nothing because we are stuck. But in deadlock we are stuck, but in live lock we are not stuck or waiting. But it's like, for example, this is a gate and there are two people here. Both of them can enter, no problem. One guy can enter and another guy can enter. But we are saying this guy is asking this guy first to you, and he's saying him first to you, and in a first to you nobody's entering, even though they are not blocked, but they block because of their behavior. Okay, so this thing is called as a live lock. But in a deadlock, nothing can happen. So how can we get out of the deadlock? Okay, firstly is the prevention. We can prevent. We will talk them in a next lecture actually, but if we discuss here simply, because we need to have four conditions in order to deadlock to occur. If we can remove out of them one of the conditions, the deadlock will not happen. Say for example, if there is no mutual exclusion, that's not possible, because if a resource is in a resource you can't have two processes simultaneously, then this is this can't happen. Okay, but if it's a hold and wait, you are holding something, waiting for another guy, so you can release that what you have taken. Okay, if we let some processes to release the resources, okay, then other guys can get out of the deadlock. Okay, so this is the kind of thing, no preemption. Okay, that means you are saying that I'm not gonna release the things. Now we are saying, okay, if somehow sorry, in the hold and wait, we are saying that we are saying here that if you are holding something and waiting for something, then you can't do that. Either you hold something, you hold all the resources together, okay, but you don't do that. You are holding something and asking for something. Don't do that. We can, if we allow that, disallow that thing, that will prevent deadlock to occur in future. Okay, in no preemption is simply we release the resource. uh, and in the circular wait, when we allocate the resources, we see that if say A asks B, B is going for C, and C is back to the A. Okay, if this thing happen, if there is a cycle coming up in a resource allocation, we disallow that last thing where it makes a cycle. Okay, we will discuss them later on in a more proper way. And there is also one thing, then when the deadlock occurred, these were the preventions. Now when it has occurred, what you will do if the deadlock has occurred? So we are saying we can preempt it. That means we don't want a deadlock to happen, so we do first something, preventive measures. Now we say the deadlock has occurred. Now what you will do? So first thing will be the preemption. So simply take the resource from one process and give it to the other. This will resolve deadlock, but at the cost of that process. Okay, that process is whatever that process done, that's lost. or we roll back. We make actually checkpoints when we do uh, the processing. We make some checkpoints, and when the deadlock occurs, we go back to those checkpoints. Okay, so we roll back, or you can simply kill one or more process. Okay, the simplest way, but it works. If you kill one process, like in a train, you kill one process. Okay, you kill this. They say this, these are the four processes. If you kill one process, that will solve, because this train can go, then this train can go, then this train can go. Okay, if you remove any of the four conditions, okay, the deadlock is not going to happen. So we'll take all these things into our next lecture. Until then, ma salam.